Flynn. Some of you might have seen me here in March when I came to talk about the FunCube satellite. I've got a bit of soft spot for 8-bit micros really, because that's what got me into my profession. I don't use 8-bit micros professionally, generally speaking, but so out of work I tend to like to play with it a lot. So I'm going to cover a little bit of history about the 8-bit micros I like, some work that others have done, and then what I've been contributing recently. So, it's a bit small, isn't it? These guys, 30 years ago, put together this thing, which was in schools everywhere, just at the time I was. But they were also responsible for something else, which probably most of you have got in your pocket. And that's the first version that came out. That's the ARM evaluation system. And believe it or not, those bottom two pieces of kit were designed to go hand in hand. So this is a little bit of history about how that happened. ARM came from, as a development from a system that was already in place with the BBC Micro called the Tube system, which allows the BBC Micro's processor to communicate with other processors completely asynchronously. The BBC Micro is known as an I/O processor because it had the VU, the keyboard, storage, all the other peripheral connections. And that other box of tricks there that you saw that had the ARM, that's known as Parasite, or the language processor. And the connection between the two processors is just done using a set of FIFOs. The asynchronous nature of that connection allows the systems to run at completely different speeds. So at the time, like the picture on the right there, you get your BBC Micro, and then you get this strange box on the side, which was optional, which would contain your second processor. And mode of operation is that both processors would boot, and in the case of the 6502, it just ran faster than the main BBC, and it copied the language, usually BASIC, across the FIFO to run out of RAM in the second processor quite a lot faster than running ROM on the standard B. But there are a variety of other processors available. There's a Z80 that ran CPM, 32016 which ran Panos, and you could even run DOS on it, and Intel. And then the ARM evaluation kit came along. The National Museum of Computing have a very nice collection of all of these boxes. You can go and see it. I was over there last Thursday. So I started looking at, if I was going to put a really fast 8-bit processor on the side of the BBC, I'm going to need this special FIFO chip called the Tube. Acorn chose a technology called ULA, Uncommitted Logic Array, which is sort of the forerunner of what we'd see now in configurable logic like CPLDs and FPGAs. And in fact, you're now starting to see that technology sort of come back in again with some of these sort of semi-FPGAs where you develop on a SRAM-based FPGA and then you go to the manufacturer and say, I'd like a batch of these done, which are non-reconfigurable. My options were cannibalising broken second-hand processors, but that didn't seem very sustainable. Some other people would have a play around doing this, and they'd use these GoDill adapters, which are a CPLD on a DIL carrier board with some level shifters. But I'd also spoken to them and found that they'd had some teething problems with it. There's another guy that's actually selling a slot-in replacement. So very similar to the GoDill, but it's specifically got the right number of pins, power on the right pins, drop-in replacement for the original ULA. And then there was a couple of FPGA-based boards which implemented the FIFOs, but they both had other problems. Either they weren't open, or they used a physical processor, and I wanted to go faster. I started looking at second processor projects that other people had started as well. And Rob Sprosen had done, down there on the right-hand side, he'd taken a modern-day ARM and put that on. That's not open. It's a good piece of kit. And he's also written his own operating system to make it boot and do something sensible. There's also, so this will be an implementation here, which is the recoached. That uses WDC 6502. I started getting interested at this point. Why were they still selling 6502s that only went at 14 megahertz when you can buy lots of other things? A lot of other 8-bit microcontrollers which go a lot faster than that. But I didn't have the answers. And I didn't know much about this at the time, and I thought the way to do it has got to be to put 6502 in an FPGA. I wasn't necessarily right though. So I visited 6502.org, and there's a lot of really crazy 6502 nuts on there. If you want to know everything there is to know about them, go there, you'll find your answer. If it's not there, someone will pipe up with the answer pretty quickly. And there's a whole subsection of forum which is dedicated to FPGA implementations of 6502. I've listed some there which will clock fairly fast, a lot faster than physical 6502s. I still didn't think this was actually that fast, because there are other soft processors going on 650 on FPGAs which go a lot faster. Some of these implementations are timing accurate. They were designed to be a drop-in replacement for a physical 6502. Some of them are code accurate, and some are astonishingly both. I found that the fastest implementations, though, are only code accurate. And that's when I started realising, by reading a lot of this stuff, there's a reason that we started off 30 years ago with a 1 or 2 megahertz 6502, and the physicals are still only at 14 megahertz. And just, I was actually just looking at the picture of the flip-flop on the previous presentation, so I just dropped this in, I edited it while I was watching. Flip-flop here is some output, goes through some combinatorial logic and feeds either the same flip-flop or another flip-flop. As the complexity of this combinatorial logic increases, the propagation delay increases massively, and it's inherent to the 6502 architecture that there's a minimum amount of combinatorial logic you can have between flip-flops. So it doesn't actually matter how fast you can clock this flip-flop. If it was in a tight feedback loop, it would go really fast. This is the limiting factor, and it's architecture dependent. And that's why all fast processors nowadays are RISC, because that fixes the architecture dependencies. 6502 is not well suited to going fast. So I was going to have to opt for 100, 120 megahertz in my FPGA. I started looking at FPGAs. Wanted a new project, didn't want to use any of the other hardware because it wasn't open. I came up with 2 candidates. I didn't go for the smallest the processor would fit in. I actually found that I wanted a lot block RAM so I could run a full 6502 memory back in internal block RAM. And those, the LX9 and the 15 size Cyclone 4 are the smallest that you can get, which you've got full 64K of block RAM. And they also handily still come in QFPs, which are sort of fairly easily hand solderable. So this was my first stab at doing a board. Just in case I decided I wanted a bit of extra RAM, I put external static RAM, but I can still boot the whole thing off the internal RAM if needed. So I can leave that external RAM on the left-hand side there completely unpopulated. And I've got 2 voltage domains really. Up the top here is the legacy, goes back to the VDC, which is all 5 volts. And everything down here is on 3.3 volts, apart from the core FPGA, which is 1.2 or 1.8 volts. And level shifters there between the 2 domains. I realised that there was a lot of work to do a complete processor, so I wasn't going to reinvent the wheel. So thanks very much to Arla. I chose his core, it works really well. Code's completely open. Ed Spittles as well, who I met at the Vintage Computer Festival in 2010 at Bletchley Park. We had a discussion. He was the guy who was doing the Go Deal adapter. He's made his code open as well, used that. I've kept all of the Verilog portable, so I can very easily port it between Xilinx and Altera, and I'm actually doing boards with both. Making sure that I didn't use intellectual property blocks, which is really easy to do, especially if the manager's jumping up and down and saying, Everett, quick. It's easy just to press the right, generate, you need one of those, and then you're locked into one vendor unless you want to spend a load of time ripping that all together. So, in my own time, I had the luxury of being able to get that right. And I really wrote all glue logic, all the RAM code, and rewrote a load of Ed's tube code because he was looking for a drop-in timing compatible replacement. And I was looking for something that was going to work with RLAT's 6502, which is not timing compatible. So to write on the other side to make it synchronous. Yeah, so hardware works. It's small enough so you don't need a huge great cheese wedge by the side of the BBC Micro. That's the underside of the BBC Micro, and the whole PCB actually slides onto the IDC connector. So there's no ribbon cable inside. You don't even need a box for it or a power supply. It just leaches its power off the big. I've tested the HDL code. Is properly portable. It boots. Just is it going to reappear at some point? Oh yeah, great. So many. Resolution's a bit better without the projector plugged in. But ran it all completely in the simulator to start with. Sorry about the resolution. You can come and have a look at that on the laptop later if you want. And my goal was that the original tube OS for 6502 runs really fast. The BBC Basic works really fast. I've got some code which I've been running in a B simulator on a PC, and it's nice to be able to run it faster than that almost on real hardware. Why did I do it? Just because I could. There was no real reason for it.
This reason, of course.
Next step is because I never had my hands on a Z80 second processor. I've got a genuine Acorn 6502. I'm going to port some Z80 HDL to the same hardware. So hopefully just by the flick of a switch you'll be able to go from a 6502 to a Z80 second processor. Just basically refresh the contents of the FPGA and press the reset button and off you go. And then produce a batch of boards. So I've only got the one board at the moment for each platform. Somewhere I've got probably thinking about equally as bad. Yeah, and that's the actually results of the thing running on my checking the results on my logic analyzer. It's actually producing proper data on my logic analyzer. Yeah. So any questions? Yeah.
So I'm absolutely fascinated. I had to declare an interest. I worked for Acorn Soft in the year the BBC Micro came out.
Yeah.
Because it's very personal. The 32016, which then became, or the 68032,
Yeah,
which then became the 32016,
Same thing,
was going
as
to
I
be our
understand it.
salvation.
Yeah.
And National Semiconductor managed to get their arse in here. What would really, I'd love to see, have you got any vision, have you got any plans to do the 32016 one? Because that's the one that we always go to tell that Solvent would save us. And I've actually never seen one run.
No, and my understanding is that the documentation for that processor is almost impossible to get hold of. There are some rudimentary, not HDL implementations, but software simulators of it, and they're very, very incomplete. They won't run anything sensible.
But so I don't remember, they never actually got the chip to work.
Yeah.
So it's a non-chip.
Yeah.
Well, it's just we had one where I worked, but I don't know if it did anything very useful.
Well, yeah, I mean, there were these sort of, they got to, I don't know, they had about 7 or 8 revisions of the silicon before they, and it was all very flaky. But it would be, I mean, it should be fantastic to see something they could never get going 30 years ago and actually work.
No, it doesn't interest me. It doesn't interest me. If
Not lots of
Probably the next thing is to go for more speed. So I'm sort of tempted, especially after now genuing up about a little bit more about CPU architecture, is to actually do my own RISC core.
Well, we look forward to seeing that one at the National Museum.
No, my goal, if I'm going to spend any extra time, it will be to do my own RISC core from scratch and then a rudimentary operating system.
And if I'm right in saying the first ARM cores ran with the BBC Micro as the I/O processor.
Yeah, that was the picture I showed on the front
Yeah.
page. Yeah,
Yeah.
ARM evaluation system,
Yeah.
and they've got the original prototype there.
It's all out patent. Well, it's 30 odd years ago.
The original cores, yeah, which aren't really that useful to run much on, because the instruction set has had changes and enhancements.
It would be quite fun to do an old second processor that could run like a 1 GHz ARM and run the original ARM BBC Basic on it. So that was damn fast in its day.
Well, Rob Sproson's got physical, I think it's an NXP in there, or something like that. I think it's 250 meg ARM. And he's got that running a port of the original evaluation system, operating system. I think he's rewritten a fair chunk of it.
So if you get the Z80 one going,
Yeah.
have you got any of the software that runs on it? Because I don't think I understand.
I'm going to have to get a loan of original CPM lists from someone else.
Yeah, I might have it. I think I've still got a Z80 coprocessor in my VUCV, which I haven't managed to find a home for. So
Well, if you're short of cash, they go for good money on eBay. Probably get over 200 quid for that.
really?
Z80s, because they're a lot rarer
Yeah.
than 6502s.
Because presumably
For over 100.
I presume I was running CPM on it. I can't even remember. Yeah.
Presumably my limiting factor in go faster is the speed of the BBC. So if you actually want something impressive, you make a BBC in FPGA that's got really, really fast graphics.
Yeah, well, Mike Sterling has done a complete re-implementation using the DE1 or 2. And he's got bit files on the website, you just plug it in there. I contributed some code to that because I can't remember if it's the DE1 or the DE2, it's got a VGA port on it, and he was just doing RGB out of that. And I hacked that to use one channel of the RGB as luminance, and I created a chrominance subcarrier inside the FPGA, and created I used basically a 1-bit DAC to clocking very fast to get there.
Is the original BBC Micro ULA publicly available yet?
There was 2. There's a serial ULA and a video ULA.
Because
In the original Model
that was the
2.
big thing about the BBC Micro. It had this new technology called ULA that
Yeah.
encapsulated all the peripheral electronics.
Yeah, it's two. There's one that does video and
Yeah.
one that does serial, which is used for the async port and a cassette port. And they're basically both so degenerately simple, you can re-implement it in HDL from the user guide. If you've got an advanced user guide, it basically fully describes the contents of that.
Thank you very much.
You're welcome.